Welcome to the introduction to the BDW API, one of a series of basic training videos for the Synthesizer high-level synthesis workflow. In this video, I'll introduce the basics of the API and show you a relatively simple implementation of a tickle script that uses the API to provide real analytical value. Let's start out with some definitions. BDW means Behavioral Design Workbench. This is a sophisticated technology that works in conjunction with the Synthesizer high-level synthesis tool. It includes many tool integrations, automation, and analysis programs. API means Application Programming Interface. In this case, the API is a collection of functions that can be used to interact with a database of information generated each time Synthesizer is run. There are a number of computer languages that can access Synthesizer results databases, but in this discussion we'll restrict ourselves to the most common language used for this purpose, and that is Tickle. Let's take a look at how the API fits into the Synthesizer tool flow. The most central part of the Synthesizer HLS flow starts with a behavioral design description written in System C and a series of constraints and configuration settings in a project file. These elements are input to Synthesizer, and we get a range of Verilog RTL implementations that are passed on to standard backend flows. Now, Synthesizer also generates a database that contains a lot of information about what happened during the Synthesizer run. So a secondary execution flow is fully supported and allows you to write tickle scripts that use the BDW API to interact with the Synthesizer results database. The most common use of this approach is to perform analysis on your Synthesizer results in order to understand in more detail what occurred during the Synthesizer run. In order to understand the API, let's look at a script that solves an actual analysis problem. Our goal with this script will be to try to understand the complexity of the design we just processed with Synthesizer. Sometimes we have a design result that is too big, or we have a runtime that is too long, and development becomes unproductive. So we ask the questions, where does all this area come from, or what is making this design take so long to process? Our goal with our analysis script is to identify which threads might be the cause of our problems, and within those threads, which function calls might be more localized problems. To do this, we will report the area and operation count for each function call in each thread. The operation count is a measure of complexity and has a pretty direct influence on runtime. So let's take a look at a Synthesizer design in the workbench. This is a small example of an ALU for the 8051 processor. It's pretty simple, but will serve the purpose of demonstrating what our script does. First, I'll run the script to show you what it produces and how you might use it. Then I'll walk you through the key elements of the script to show you how you might use the BDW API. In this example, I've already run the Synthesizer configuration called Basic for the ALU 8051 module. If I now hit Ctrl-Alt-T to get a terminal window, I can type in the name of my script with the appropriate arguments, in this case the module name and the configuration name. As you can see, this produces a whole bunch of information about the function calls in the main thread. A lot of this we don't care about, so let's use the command line argument to filter out the small stuff. In our demo script, I know this is the -t argument for threshold, and it defines the minimum area threshold we're interested in. So let me set a threshold of 5, which will filter out all of these function calls with 0 area. And now we get a much smaller, more useful set. Here you can see each function call, a guesstimate of the area required for the call, and the number of operations included in each. Let's say my problem is one of runtime. In that case, I'm not really interested in the order of these calls as they're printed here, which is sorted by area by default. I'm more interested in which function calls have the most operations, or ops as we call them. So let's sort the data by function call operation count. This is the argument SFO. Now, we see that the doSub function has the most operations. Let's go take a look at that. And here we see that there's a bunch of logic in this function. One approach to reducing the complexity that Synthesizer has to deal with here is to add a dpopt inline directive in this function. Let's see what that does. And if we go run Synthesizer again, we'll get a different result. So we can go back and rerun our script just like we did before, and we see that the do subfunction call now contains only one operation. All the previous complex operations are now wrapped up into a single data path component, and this will make processing the design much simpler for Synthesizer. So we see that our script is very useful for providing us with real actionable data. Now let's take a look at the script itself. This script is written into the file threadcomplexity.tcl. Here at the top of the file we see some shell magic that allows us to execute this script as if it was just a direct Unix command. I also like to use the command line package in the script to process the command line. It's a very good set of utility functions for processing command line arguments. Here we see there is a print help function which is executed anytime you type in the -h command or anytime you type in a command line that is illegal for this script. Let's go to the bottom and see how we would start the program. Here's the main section. Here we define a few variables, process the command line. Most of these command line options specify the sort order that we want the data to appear in. And here we save the last two arguments as the module name and the configuration name for the script. The rest of this section deals specifically with preparing the API for execution. This first section creates a BDW project object based on the project file name. Now we're going to get some of the data for this script out of the project file and some of the data out of the log file. The first set of data we're going to get out of the project file, and that's going to be the module object and the synth configuration object. So we first get the module object based on the name, and given that module object, we then get the synthesizer configuration object corresponding to the given name. Once we have this configuration object, we can access the log file database and get a handle to that object. Once this call is complete and succeeds, we will call our function that does all of the work, the dump thread complexity function that you see at the bottom. So let's go take a look at that dump thread complexity function, which is really the meat of our program. This function is really split into two separate pieces. The first part extracts the data from the database, and the second part formats it and sorts the columns into the order in which we specified on the command line. This first section looks in the log file for threads. It filters out anything that's a method, and then for each thread it extracts the function calls. For each function call, you can see it collects the area, it collects the name, it collects the line number, etc., various different attributes of the function call that are contained in the log file. When all of this data is collected, we move on to the formatting side of things. This is just straight TCL. This doesn't use any of the API functions. And for a capable TCL programmer, this will be very straightforward. All in all, this script is very straightforward and pretty easy to implement. Now, other resources are available to help you understand the more complex nature of the API. With the latest version of Synthesizer Workbench, we've included the Synthesizer BDW API reference guide. This reference guide gives you complete documentation on all of the different objects and their member functions that are available to you through the API. The front page of this reference guide contains a number of small examples of how to access the most common objects in the database. Let's review our script and the difficulty of creating it. Overall, it's about 289 lines of code, including comments. Trivial stuff like processing command line arguments and the help function make up about 103 lines of this. Setting up the API and getting object handles of the module and synthesizer configuration are another 26 lines of code, and our complexity analysis function is the meat of the program, making up 136 lines of code. Of this piece, the data collection, which makes the heaviest use of the API, is 68 lines of code, and the data formatting is 50 lines of code. So this is a very small program that provides useful, actionable information by leveraging the power of the API and the access it provides to the myriad of details about what happened in your synthesizer run. That concludes our video of the introduction to the BDW API. I encourage you to take a look at the BDW API documentation that is included as part of the Synthesizer workbench and experiment with the development of your own useful scripts.